It has been a pleasure for me to participate in the Hawking Radiation Conference and spend a week of intensive discussions with old friends and colleagues on fundamental problems in black hole physics. It is many years since we experienced similar excitement on this topic, in the 40 years since Hawking radiation was discovered. As is often the case, a breakthrough in an important field creates a set of new and more difficult puzzles. In this case, the discovery of Hawking radiation led to the mystery of the information loss paradox. Soon after I discovered that black holes evaporate, I realized, since we cannot measure the quantum state of what fell into a black hole, then we could not recover this information when the black hole had completely evaporated. I raised this concern in my paper Breakdown of Predictability in Gravitational Collapse in 1976. There has been a whole body of literature dedicated to the information loss paradox ever since. Various attempts to solve the problem have been tried and have, so far, failed. The problem was recently referenced in the more dramatic description of firewalls blazing around a black hole. In January 2014, I suggested that black holes may not exist at all. Such a possibility requires a precise understanding of the origin of Hawking radiation and implies that singularities do not exist. The singularity theorem can be evaded by quantum effects. We heard 3 talks on Monday by Thuft, Mersini, Houghton, and Bardeen, exploring such a possibility through backreaction. The overlap approached in the 3 proposals remains to be further explored. Hawking radiation observed at future infinity is produced by vacuum-paired radiation near the surface due to the changing gravitational field near the collapsing star, as I described in 1973. The precise location in the exterior, where paired radiation takes place, cannot be given accurately since particles lose meaning in curved spacetime. But the stress energy tensor is well defined locally. The process is asymmetric and the collapse phase is crucial to particle creation and the breaking of symmetry. When the star has collapsed into a black hole, the horizon temperature is given by the temperature of the thermal bath of Hawking radiation. The average wavelength of the produced particles for a star with mass m is about order m, and the time interval during which the star collapses is of order inverse of m, and thus the uncertainty principle is satisfied. Black holes are not stationary. They evaporate, albeit very slowly. A solar mass black hole takes about 10 to the power of 75 years to evaporate. Since black holes evaporate, the process of paired creation continues, although at an incredibly low rate. Indirect evidence suggests that black holes exist. We will soon know the answer to this question observationally when data from the Event Horizon Finder experiment becomes available. Even if black holes exist, information about the particles that fall into them is not lost. I described my proposal on solving the information loss paradox on Tuesday. The solution to the information paradox lies in the supertranslation invariance of the gravitational scattering matrix that connects the ingoing and outgoing particles. I realized that the BMS symmetry, with supertranslations as its subgroup, can be defined on the horizon of a stationary black hole. Every time an ingoing particle falls through the horizon shifts by a certain amount. A supertranslation moves each point of script I plus a distance alpha to the future, along the null geodesic generator of the horizon on script I plus. This is equivalent to the advanced time v being shifted by an amount alpha, where alpha is a function on the two-sphere. The information about the horizon shift induced by the incoming particles falling through the horizon is stored in the supertranslation. This corresponds to a delay in the emission of the WAV packet registered as part of Hawking radiation at script I plus. The information about ingoing particles registered in the form of emission delays of the outgoing particles is scrambled. Although scrambled, this information is fully recovered since the scattering matrix is supertranslation invariant, and thus preserves unitarity. A cutoff of high-energy modes near the horizon is not needed. I conclude that the solution to the information loss paradox is supertranslation. This solution to the information paradox can be applied to a black hole on any background, including those that are not necessarily asymptotically flat.